You've described your work in a nice concurrent way. You've got this embarrassingly parallel patterns on top of it. And you can start doing these kind of designs with confidence because you understand how to describe work in a way that can get done in large scale systems.
Hey there, welcome to Book Overflows, the podcast for software engineers by software engineers, where every week we read one of the best technical books in the world in an effort to improve our craft. I am Carter Morgan, and I'm joined here, as always, by my co-host, Nathan Toops. How are you doing, Nathan?
Doing great. Hey, everybody.
Well, thanks for tuning in, everyone. As always, make sure to like, comment, subscribe wherever you're at. Give us a 5-star review. If you're on an audio platform, share it with your friends and coworkers, anything to help grow the podcast. We've been we love making the podcast, and we've had a lot of people reach out and just say, hey, I'm a regular listener and love hearing from you guys. And we love hearing that too, because, this podcast is still essentially a hobby at this point, but, it's fun to hear that it's resonating with you guys. And thanks everyone for tuning in. Last week, we did our special kind of on the Georgia Tech OMSCS program, in particular, the graduate algorithms class, which is sort of legendary there. Thanks everyone who's commented on that. We've gotten a couple emails about it too. It's just really cool to see that it's resonating with people. And we've seen a couple people even say like, oh man, I was considering this program, or Nathan, I just got this email last night, so I'll have to share it with you. But it's just a guy who said like, I didn't know you guys had non-traditional backgrounds, and I'm also a father. I got 2 children. I'm the primary breadwinner. I didn't know. I don't want to waste money on like a diploma mill. And so he was really intrigued by the Georgia Tech stuff. So all this podcast did was prompt one guy to go into the Georgia Tech program. Then, that's something.
Yeah, that's cool.
So, thanks everyone for tuning in. It's cool to see all of that. And thanks for indulging us, because that was definitely a bit of an indulgent episode, kind of just talking about our school and our program. And you might be listening and saying, don't these guys usually read books? And that is true. We do usually read books. And we're back to books this week with a great book. This is a great pick by Nathan, actually picked this one. Grokking Concurrency by, I believe, Kirill Bobrov, K-I-R-I-L-L. We're going to say it's Kirill. Let's give the introduction for him, and then we'll give you the book introduction. Kirill Bobrov is a seasoned and slightly grumpy software engineer who knows the ins and outs of developing and designing high-load applications. With a passion for data engineering, he now dedicates his efforts to implementing cutting-edge data engineering practices for companies worldwide. And guess what? This grumpy individual is also the cool cat behind the popular illustrated tech blog, luminousmen.com. And the introduction to the book is Grokking Concurrency is a perfectly paced introduction to the fundamentals of concurrent, parallel, and asynchronous programming. In it, you'll learn the practices you'll need to program multi-core processors, GPUs, and other high-performance systems. Author Kirill Bobrov skips the math, jargon, and academic language and concentrates on clear, plain English explanations. And just a note, after reading this, I'm even more impressed with this book, and we'll talk about how impressed I am, realizing that Kirill is not necessarily an academic, because this book really does get into it. It's got a good balance between like the details and but not being like too nitty gritty. But we can talk about that in just a sec. Nathan, what are your thoughts on? We read the first half of Grokking Concurrency. We read through chapter 7, about halfway through the book.
Yeah, this gets us right into the beginning of section 2, which sort of dives in deep on some of the juicier topics. I thought this book was a lot of fun to read, and I think that's not always common in straight up software engineering books. This is, we've kind of oscillated back and forth with some, sort of more businessy type books, or books that are kind of, around personal development. This is, for the folks requesting in the comments, this one's straight up a fantastic software engineering book. I thought the pacing was really good, and I appreciated, I think I've talked about this in the past, where like a lot of times they'll start with lots of specifics and then get very abstract later in the book. He does something that I wish more books did, which was concrete example, philosophy behind it, coding example. And I think that that's actually like a really nice way to kind of have the idea solidify in your mind, because you kind of need the concrete idea behind it and the philosophy to read the code. At least I do. And I thought that was really useful. It's also not my favorite programming language for using concurrency. He uses Python for concurrency. And so I'm a Go programmer. Concurrency is like built in from the ground up. But I think it's a really wise decision, even coming from somebody that's a Go developer, and he speaks very highly of Go in the book. But Python's very approachable, and I think it's very easy to read regardless of which language you're coming from. So I think it was a wise decision to pick Python for this book.
Yeah, I really enjoyed this book. We're still reading it. I think, like you said, Nathan, I mean, we won't name names, but we've had some programming books on this podcast that even though I really liked the content out of it, reading it was a slog. And I just remember one in particular where like I had left it, I slacked off and had to read like 120 pages of it the night before the podcast. Yeah.
like any good procrastinating student.
Yeah. And I was just like, oh my gosh. I feel that way. My brother, because I'm a big fan of American history in particular, like, well, I guess any sort of American history, and especially American like presidential history. And my brother gifted me the biography of Ulysses S. Grant, who I think is a really fascinating individual, by Ron Chernow. And that is the book I read when I want to fall asleep. And I always tell my brother, I'm like, I want to know everything in this book. Every time I read it, it's fantastic. And it's just so boring. And we've had books like that where I'm like, I want to know everything in this book. It's not the greatest reading experience. This is not this book. It's really, I don't know how you make a book kind of like as dense and as, I don't know. There's a lot of great stuff in here, but it's breezy.
Exactly. I'd love to study the structure of this book more. Also, he does draw pictures like on his blog, and those same pictures are in the book. And that also makes it fun because they're like really well formatted, information dense diagrams that support the thing that he has coming up. And some of them are just like kind of funny pictures, but the other ones that are like talking about, oh, how you would pipeline data, and we'll get into some of that. And later it's like, oh yeah, that is what we're doing, isn't it? Like this is really, it was really cool.
Explaining like the difference between like different CPU core strategies, right? Like,
I'd never seen SIMD and all these other ones visualized. Yeah, exactly. I'd never seen it visualized like that, and I was like, yeah, that is how it is structured. That's really nice.
So very, very talented. And again, I think all the more talented. We actually looked up Kirill just before the podcast, and he's a senior data engineer at Spotify. And so this is not someone with a, well, I guess
speaking of big data, I can't imagine what it's like to comb through the analytics data at Spotify.
I know, right? I'm just trying to see. I guess he has a master's degree in information and communication systems. I was curious if he had a PhD. Because I mean, this is, I would say, like, to me, this reads like a seasoned academic could have wrote it. So very, very cool stuff here. And for me, it's kind of felt like a trip down memory lane. I took an operating systems class at Georgia Tech, in particular, because this was the kind of stuff I wanted to know. And so it was nice reading through this. And I've learned definitely some things I didn't know quite before, but a lot of the basics of concurrency, like that was a big, that was something that was really missing for me. And one of the reasons I kind of felt prompted to get a master's degree, because I was like, I'm a software engineer, but I don't really know, like, I don't know what a thread is. I don't know how they get scheduled. I don't know what's a thread in a process. And so that was really eye-opening for me in my operating systems class. And this book does a really good job of explaining it too. So some of it has been a refresher for me, but I think this would be great for anyone who's kind of feels like I did, like maybe your operating systems background isn't as strong as you would like it. So lots of really, really cool stuff in here. We're going to try to cover as much of it as we can. Stay tuned for the rest of it, and we'll be right back. And we are back. Thanks so much for tuning in. So let's talk about concurrency. I guess the first thing we should mention, Nathan, is like, what is concurrency? And I guess at its core, it's really just running multiple tasks at the same time. He draws a difference between parallelism and concurrency. And I believe, Nathan, how does he define that?
So he mentions, there's a really famous talk, and I'll probably put the link in the description. Rob Pike, who is one of the creators of the Go programming language, has a really good talk called Concurrency is Not Parallelism. About why they're related, but they're not exactly the same thing. And I think I'll give you sort of my Cliff's Notes version. concurrency is a way of describing work. Concurrency may not be parallel in the sense that if you have a single processor and it can only do one thing at a time, what concurrency does is allows you to describe how work is being done so that you're still doing one thing at a time, but you're breaking up the work into chunks that are understandable to the workload. And we can talk about why single-threaded things can have concurrency patterns that actually can be more performant than non-concurrency. A perfect example is like JavaScript waiting for something to happen on another remote server, right? It can basically tell itself, oh, go get this thing, and then when it's ready, pick up where I left off, right? I'm describing a piece of work. Now I have no control over how long the thing off processor takes or these other things. Parallelism, on the other hand, you can write parallel code that's not concurrent. That can be you run the same process on different batches of data and then spin those up independently of one another. They're all running in parallel, but there's no description of concurrent work. None of those processes have any idea what's happening across the other one. There's no coordination or anything like that.
Interesting.
Yeah. So, and again, I think he talks about this later in the book, but I actually like the washing machine idea, which is like, most houses have a single washing machine and a single dryer, right? And so you can describe your work concurrently in that I say, I put clothes in the washing machine. I put clothes that have come out of the washing machine go into the dryer. Clothes that come out of the dryer go to be folded, right? Now that's always going to be done one after the other if you have one washer and one dryer and one folder, right? But you could break these up into concurrent operations where I say, oh, actually, I have a washing machine and a dryer, and as soon as I take clothing out of the washing machine, put it in the dryer, I can actually start another load of clothes in the washer, right? So I don't have to wait for the dryer to be done to start my next load in the washing machine. And so we can describe this in a concurrent way. But let's say I'm at a laundromat and there's 8 washing machines and 8 dryers. Well, that concurrent workload that I've described, I can actually also parallelize them across 8 washing machines, right? And if you've written your code in a concurrent way, it's very easy to find what they call embarrassingly parallel. And he mentions this in the book. It's a term I abuse and abuse. Anybody who's worked with me, I'm always like, find the embarrassingly parallel thing here. And we can talk about that in a minute. But yeah.
Well, so yeah, that's a little bit of what kind of concurrency is, just to start us off. He talks about the importance of concurrency and like the history of computing. Basically, when we were starting out, I say this like I was doing this, but when we as humans were building the first computers and building in particular the first, CPUs, we kind of thought, because a CPU consists of transistors, and those transistors are what kind of allow you to perform the logical operations of a computer. And so we kind of thought, okay, Moore's law, right? We could double the number of transistors we could fit on a chip like every year. And so we kind of thought, okay, we'll just keep doubling and doubling and doubling, and we'll just keep adding more and more transistors to our chips, and we'll just have these supercomputers one day. And then as they started adding more and more transistors to the chip, they realized that, and we couldn't quite figure out what exactly the limit is or why there's a limit, but there is a limit. There's a limit where we don't, Nathan, do we have a theory?
Yeah, no. So there's a couple things. And again, this is my like armchair physics understanding. So part of how we doubled the transistor count was the really cool method where we would actually like cut the size of the transistors in half, right?
Yeah.
So and they would get smaller and smaller, closer and closer together, and we would have a transistor density that was deeper. Well, there's a limits to physics, right? There's like how much, and you start running into the limits between classical physics and quantum physics, where electron behavior starts getting unpredictable once things get really small. And you may have heard the different things like 5 nanometer, 3 nanometer. As these get smaller, they're harder and harder to manufacture. And they do amazing things as far as latency and all these other pieces. But Moore's law, as far as like, one of the things you probably have noticed, especially if you're younger, is that, CPUs are kind of hovered between like cheap CPUs are around 1 point something gigahertz, and really, really nice CPUs can get up to like 5 gigahertz. But you don't see a double. When I was growing up in the 90s and early 2000s, you would see a doubling in clock speed. You would see a doubling in clock speed in Moore's law, and then it kind of hit a plateau. And then they started doing multi-core, right? And then they were like, oh, well, that's how we'll increase the transistor density. But we didn't actually talk about transistor density back in the 90s. We would just say Moore's law is going to double clock speed. But we don't have 8 gigahertz, 16 gigahertz, 32 gigahertz processors. That would be amazing, but there's heat limits. That's one of the things that, it used to be that you didn't really need much heat dissipation on processors. Apple kind of came in and did some weird stuff recently, which is that like Intel ruled the world and they had bigger and beefier fans on stuff because we would just deal with heat loss that way. And then Apple went back and like made an inferior processor, right? The ARM processor was not great. They used it for mobile devices, but then they've had some breakthroughs in performance. And like, my wife just got the brand new MacBook Air, right? Which is
my wife has one too.
The M4 processor, no fan, right?
Yeah,
it's so fast. It is an incredible piece of hardware, and that's some amazing engineering that went into it. But we're still hitting the limits, right? And yes, we're getting some clever breakthroughs here and there. But one of the things we can do and get around the cost limit is add more processors. We can scale horizontally. And that gets us into why, if you've written your code in a concurrent way, if you've written it so that it can be parallelized, you can horizontally scale your workloads instead of saying, oh, well, we can't do this today, but in 2.5 years, when Moore's law comes in, I'll be able to double the clock speed and then my code will be able to catch up. We can't write code like that anymore, right?
Yeah, and kind of, this is like CPU 101. Again, read the book if you want all the details, but basically, we're all familiar kind of with memory in a computer, right? Most of our memory is stored on, the disk, the external drive, or whatever, the solid state drive. We all know about RAM too, which is easier and quicker and cheaper to access. But each individual core also has their own little chunk of memory, and that's used for again, I'm not familiar with all the exact details, but that stores the memory it needs immediately to be executing the logical processes. And so that means that each individual core is isolated from all of the other cores. And so each core can only essentially be working on one thing at a time, one process at a time. And we'll talk about later time slices and interleaving processes. But that's kind of the point we've hit with our computers is our computers, a modern computer have 8 cores. I mean, like a MacBook, I think the highest option you get is 16 cores. I don't know.
Let me see what I have now. I'm on the latest. I've got the M4 MacBook Pro. It's not like it's the Pro version, not the Max version. So
I'm seeing at least the M2 all have 8 CPU cores.
Yeah, I think I have more than that. I think I have like 12.
Yeah, you have 12. Okay.
Yeah. And another thing we're talking about in this book is GPUs, which is something I've spent less time with, but if you're in machine learning world, is incredibly important because they're not good general purpose hardware, but if you can do massive parallel operations, and one of the things they talk about is what's called SIMD, which is, let's say you have a big vector or big array, and you can do independent math operations on each one of these like floating point numbers. If you can do those, you can, some of these have, thousands and thousands of CUDA cores, and each of those can do these floating point operations in parallel, right? On a CPU, you're still doing it sequential operations per core. They're very fast, but if you're dealing with millions of parameters, it's much nicer to have a shovel that can handle thousands at a time, right?
Yeah, from what I was reading, a CPU basically has fewer cores, but those cores are more advanced. They're programmed to be able to execute lots of different kinds of instructions. A GPU might have hundreds or thousands of cores on it, but they're very, very simple. And so it's one of the funny things. We call them graphic processor units because that's what they were originally designed for, video rendering, real-time 3D graphics. I'm not familiar with all the science behind that, but essentially it needs a lot of cores processing a lot of really simple operations. Like you said, Nathan, kind of massively parallel stuff, but they've become transformational for large language models again, I'm not familiar with everything that goes into training a large language model, but I do know that at some point you need to do a lot of math, a lot of kind of very simple math.
And it's a lot of matrix stuff, right? So you're basically saying, I'm applying this, this change in the vector across these parameters. And, again, this is where the book, I think, even if you are not as comfortable with the CPU and GPU side, what's really nice is he frames it into just like how you structure work. And I think most of this book progressively builds on the fact that you say, okay, this type of structuring of work is valuable, and here's why it would be valuable under this context. And a lot of this book is one of those where it's like, is this a good pattern? Well, it depends, right? So it's like, if I can structure the real world work that needs to be done, this is a pattern that might be useful, right? And this is one of the things that I've in my personal journey, because I'm a Go programmer, these conversations inherently come up. I mean, to take full advantage of Go, you really do need to wrap your head around how mutexes work and how channels function and how you pass information across your workloads. And I think that it's really brain bendy to start doing concurrent programming. And I think it's a good stretch for any programmer. If you've mostly been doing very linear programming, it's really important to kind of break your brain a little bit and think about, is this really the smartest way I could be structuring this? Or is there a way that I could describe this work so that it actually becomes much more efficient, feels snappier, because I'm maybe waiting for something that doesn't need to be waited for, right? Like that's the sort of big aha moments that come out of this book.
Yeah, absolutely. And so that's what a lot of this book is about. Is like, okay, how, knowing now that we have concurrency, because that's the idea behind concurrency, right? Is especially in modern computers, we have lots of different cores, and so you can split your task up among many different cores, whether that's generating more processes, generating more threads. But it's not always as simple as, okay, I'll just make 20 of these things and have 20 execute at the same time. There's, like you said, we have to communicate, you have to coordinate. And so that's what this book is about. It's like, okay, how do we think about our programs to understand when something might be, like you and Kirill say, embarrassingly parallel, or when might you need to have more kind of sequential ordering and some logical constructs in there to keep things flowing at the same time. So I guess, what do we want to hit next, Nathan?
Yeah, I think touching on the embarrassingly parallel thing, you've probably heard this term and maybe we're too afraid to ask. So embarrassingly parallel is a description of when I can parallelize something in which those parallel processes don't have to communicate with one another. This actually gets us into Conway's law, and I think that actually this is a good piece here. If you're an organization and it feels like the decision-making process is very slow because you're having to constantly coordinate with, like, let's say, executive leadership on every little thing that you're doing as a programmer, you're probably not embarrassingly parallel, right? I'm having to go back and have a meeting about a meeting to get unblocked on some decision that my team is trying to make. And you can think of this as like inter-process communication, where for my team to go to its next step, I actually have to get unblocked by another team up here, right? It's much better organizationally if I could actually set a directive of what's the goal of the thing that this unit's trying to do, and then let them operate independently up to some checkpoint. And what that independent operation is the embarrassingly parallel part, right? So I can scale to 250,000 employees if I've got chunks of, let's say, 8 to 10 engineers that are operating independently with certain checkpoints coming back in between. I can get a lot of work done at the same time. If you're 250,000 engineers and the CEO has to weigh in on decisions, you're going to die, right? Like you're just never going to be able, you're going to be so blocked up by waiting that you'll have resource contention. And so, yeah, I think that this is this idea, and I think what you brought up with the CPU and the different layers, right? L1, L2, and L3 cache, then going into memory, and then going into storage, and then going to like network access. Each one of these, I remember seeing a diagram a while back. It's not in this book, but it's basically like the equivalent of, going to your mailbox and then like going to the state capitol in your state and then like going to the moon and then
Well,
like go
let me
into
share
another
that because
universe.
I've got
Yeah.
it pulled up in the book, and
Oh,
that
cool.
was really eye opening to me. So basically, he says so one CPU cycle takes 0.4 nanoseconds, but he scales it up. He says, let's say one CPU cycle takes 1 second. That means an L1 cache access takes 2 seconds. L2 is 7 seconds. L3 is 1 minute. RAM access gets up to 4 minutes. And again, we started at 1 second. High speed solid state drive IO operation, 7 hours. Then just regular solid state drive IO operation, it says 1.5 to 4 days. A hard disk drive IO operation, 1 to 9 months. And a network request, San Francisco, New York City, 5 years. So that is the difference. If you think of one CPU cycle as 1 second, a network request is the equivalent of 5 years. And it's like, dang. And really, we're talking about 0.4 nanoseconds to 65 milliseconds. But it's like, holy cow. That is, I never even considered the scale like that.
Yeah. And I'd run into, when we started doing, I was at a fintech company and we really started realizing these optimization paths of where we got data from and the locality of that data. When you start dealing with data at scale, these become incredibly important to think about. Sometimes you need to have that long time period because correctness, like let's say I always have to get data from the database because the database is the only authority that I ever trust. You understand that you're going to have to deal with that network access, super long latency piece, even if you're dealing with like a high performance network. Like even if I'm on a 20 gigabit network with, everything's got NVMe drives and all these other things, you're still throwing incredibly powerful stuff at a very slow operation versus can I keep something inside of the CPU in the L1 cache, right? And you started getting into weirdly, again, somebody who's doing Rust programming or Go programming, people obsess over, is it in the heap or is it in the stack, right? Am I actually having to do memory allocations for this little piece of data? And that might sound like over optimization, but in some code paths, it's not. I mean, I remember one time I was doing some analysis on some code that was running slower than I thought it should. And I realized one of the libraries I was using had was doing a bunch of memory allocations that I didn't intend. And I refactored that code so I wasn't doing the memory allocations. And I think I got like a 100x speed up with this like hot code path that I was doing. And it made a huge difference. And it wasn't until I wrapped my head around the fact that like, I'm thinking, oh, well, it's in RAM. Well, RAM's way faster than disk, so RAM's fine. But it's like, oh, but if I could do these operations massively parallel and never have to touch RAM, that would be amazing, right? If I can keep this in the local cache. And these are really like, when you get into these juicy problems, it's really kind of fun to solve. And then if I have it never allocating memory and it happens to be an embarrassingly parallel thing, and I'm using a programming language like Go, which has something called green threads, where we don't actually use system threads unless we have to, because system threads are also much more expensive. So it has its own memory allocator and process runner internally. And so you can end up getting these like crazy performance boosts off of the same hardware, right? Pretty neat.
Yeah, it's interesting just because like my career is kind of the total opposite of this. Like sometimes I feel like a little bit of, I don't know, like embarrassment because I don't do a lot of stuff at like this level. Like I can't remember the last time I had to solve like a concurrency problem. Like, I don't know, use async await. Like that's about all I need to know. But I'm on the total opposite side where like I'm in the Google Cloud console or the AWS console every single day, right? And I'm dealing with these massive distributed systems, which I know, is it's funny. Like that's not really that wasn't part of the job 20 years ago. So it's just funny how things change. So I mean, maybe we can talk a bit about. He calls this the building blocks of concurrency, right? And he talks about the differences between threads and processes. So a process, is and correct me if I'm wrong, Nathan, but basically any program you write is always going to consist of a single process unless you generate more processes from it, right? But everything starts as just one process.
Yeah. So a process, and if we think of it from like a Unix standpoint, right? This is like this is something that's running in that Unix environment, right?
Yeah.
That's the process that's running. Yeah.
Yeah. And so, every process is going to have its own set of resources, in particular, its own memory space. And so, that's the little memory chunk it gets assigned on the CPU cache. And so, it can communicate with that memory space, fairly rapidly. Then there are threads, which are lightweight processes that share memory within a process. And so I believe that memory space, that must not be on the CPU cache, right? Because you can put threads across different cores. So that memory space must be on what? On the RAM? Do we know this?
I don't think it gets into the details, and I think a lot of that's abstracted away. And that's one of the things he talks about too, is that like, for instance, in his Python code, right? I've used the threading library in Python as well. You basically get this process ID that is kind of there for the different threads, and you kind of know that if the multiple cores are available, the system itself will try to find up the least used core to like throw it into. But the process ID, even though again, even in their own terminology, process and threads get like overlapped and overloaded a bunch, but they are related to each other. So like if you have a thread or a child process, those still get to share a similar memory space. But it's like there's like a parent-child relationship between them.
Okay. Yeah, but then processes, right? Because that's the trick about working with processes via threads. Like the nice thing about processes is that you don't worry about about like accidentally overwriting the other's memories. You get your own separate little chunk of memory to work with. But then communicating between processes is difficult. You have to,
because they're independent.
Yeah, exactly.
They're independent of each other. There's a lot of coordination, and I would say it's very easy to get like mixed up into stuff. A lot of bugs that are introduced, like as soon as you try to get into concurrent programming, you get into something called non-determinism. Non-determinism is really scary as a programmer, meaning that like there's a lot of system behavior that you don't have control over, and so sometimes another process or another thread might finish before another one, right? Especially, let's say that thread is responsible, or that process is responsible for talking to some network access, and let's say you're doing like 15 queries to like various websites all at the same time. We have no control how long that is going to take to come back. And so sometimes these threads will surprise you and come back in different orders. And these are the kind of things that you have to think about when you start dealing with multi-threading or multi-process work. Yeah.
Yeah, you can. I remember doing this in my operating systems class and having projects where like because you can basically instruct a thread like, okay, now wait, you need to be blocked until this resource is available. But you can accidentally write a scenario where all the threads wind up getting blocked accidentally, and then they just remain blocked forever because they can't, they're all waiting on each other. And so, there's basically two ways to communicate with each other. You've either got to do message passing, or you have to do memory sharing.
Yep.
And Go is pretty opinionated about this, right? Go has that famous quote: "Do not communicate by sharing memory; instead, share memory by communicating."
Yeah, this is like a Go proverb. There's like a whole set of Go proverbs. It's interesting too, because there's like, this is contentious. In a very strict sense, sharing memory to communicate can be faster.
Interesting.
Where you use mutexes for certain types, but it's much harder to reason about. And there's a lot of ways that you can like misbehave. And again, this is where you might allocate some memory and then throw a mutex in front of it, so that basically, in a mutex, for the uninitiated, mutexes allow you to lock some access to some piece of the system while one single process or one single thread is interacting with it, and then unlock it when you're finished. In this way, when we do have to share a piece of memory, I know that I get exclusive access to that, so I'm not corrupting the memory, because this is one of the things that can happen is if multiple processes try to access the memory at the same time, you lose track of like, the data can get changed mid-cycle, and the system, bad things happen. So I would say, let's say I access some memory map, or some map, hash map or something. those are not multi-thread safe typically. And so I would lock it and then access that memory with one of my processes. And then any other process that wants to talk to it has to, they request a lock, and they have to wait until the lock's available, right? And so that's what this concurrency is, sharing memory and using this pattern. Sometimes this is like the best way to do it. The problem is you can get something called a deadlock. What happens if my process never unlocks that code ever again, right? And I can take the whole system down across all multiprocessors or multi-threads or whatever. And there's ways, again, to do this where you have like a time to live and you release the lock after some period of time. But it's much easier to think about if you communicate, if you share memory by communicating. And what this means is they're kind of like data pipelines. And in Go, we have these things called channels, but you can do this sort of model with like semaphores and all these other kind of cool things in other languages. But the idea is a channel in Go you can think of as like a pipe, a data pipe that you can wire up across threads or across concurrent processes. And so I can funnel data from one place to the other and react to that data when it comes in. And so, and I can use something like I can pass the full-on data itself, like a copy of the data. Like I have a string and I pass that string and it copies across the pipe. But I can also pass like a pointer, right? So if let's say if it's a big data structure, but what I really want to do is just pass this through the channels from one place to the other, and that you basically get a mutex from that, right? I'm passing this pointer to one thing at a time, but it's only made available to the next thing when it's ready. And this makes the system very easy to reason about. Now I look at this worker and I go, okay, I don't have to worry about some global mutex. I don't have to worry about all these like weird lower level abstractions. I just think about the data comes into like one of these 5 channels, these pipes, and then I can process that data as it comes in. And so Go gives us like something like this. You can do like a for loop with this thing called a select statement. It's like a switch statement, but it's made for channels, where I can say anytime any data comes available from any channel, process it. And it's sort of this flywheel where I can actually take, lots of communications happening from a bunch of different places and still like process it in this like real-time piece. And again, I can build these very complex systems that operate across multiple processors and do all kinds of crazy stuff. But I look at the code and I go, oh, okay, I understand what this is doing. This is like a flywheel that's like processing data from places that maybe I don't have control over.
But like you said, that the idea of share memory by communicating, right? Having these channels, these pipes, that is slower than just accessing the same memory, right?
Yeah. And by slower, we still have to remember, like, and I would say in Go, a lot of the stuff we're doing is over the network, right? So even if it's technically slower than using a mutex, if let's say most of your channels are waiting for information coming back from the network, it's still significantly faster than the network access. So now what I get is I get a productive programming environment that's easy to reason about, easy to write tests for, and it's kind of the flywheel on top of a bunch of like maybe more expensive network activity. And I'll tell you, most Go programmers, for instance, aren't deep in channels day to day. Actually, it's considered an anti-pattern if you're having to do that. Like for instance, if you use the net HTTP library, which is the library that like gives you all the network programming, all of that uses channels under the hood. But you are just thinking about like a function handler, like you are in any other programming language. I've got a request and a response, and I'm like putting a status code, and maybe I'm putting in some logging data or something. But under the hood, the way that all of those function calls are being sorted out inside of the web server are all being done under channels and pipelines and a bunch of other kind of cool stuff. And this is why Go servers can like scale up to, tens of thousands of concurrent sessions on a single server because of how like streamlined the share memory by communicating. It's just very easy to. All I have to think about is what's this increment of work that I'm working on, and then it's handling all the data pipelining between them.
Now, you might be thinking at this point, if you're not familiar with these details, you might think, okay, wait, so every thread needs to run on an individual core. My MacBook has 8 cores. Are you saying that only 8 threads can exist at a given time? And the answer is no, because we have multitasking. And so it's kind of a funny term because you think of multitasking. Yes, we multitask it in that your computer has 8 different cores, which can be executing 8 different threads, but then the individual cores can multitask. And basically, it multitasks exactly as a human multitasks, right? By rapidly switching context between the different tasks. And
Right.
so if you create, but there's a balance there, right? Because let's say you create 40 threads for your 8-core CPU, then that means that every core is going to have to essentially handle 5 threads. And it's going to have to switch in between them. And there is, and like a human, there's a context switching cost, switching in between threads. And basically the operating system has a lot of different strategies it uses to switch in between threads. Sometimes a thread might voluntarily yield control. Like IO operations are like that. Like, something that is waiting on input will say, okay, I don't have anything to do until the input comes back. Time slicing is another one where the operating system, and you can define this too, but you or the operating system will basically say, okay, this thread gets to run for 5 milliseconds. And then after 5 milliseconds, I'll pause it and then I'll move to the next thread. But every time that thread gets paused, there is a context switching cost, because basically what the CPU has to do is it has to take a snapshot of the state of the thread at that point, all of the different resources it was using to, establish where it was at that point in the thread. And then it's got to load in the other snapshot it previously generated. And so, again, we're talking the tenths of nanoseconds here, right? In terms of how much this is actually taking. But it's worth considering. And he actually gives a really cool example of multitasking. He says, like, let's say your buddy has like an old Pac-Man arcade unit, and he wants you to program a Pac-Man game on it, right? But it's stinky. It's only got 1 core. And he says any Pac-Man game is going to have like bare minimum 3 threads. You got to have a thread for rendering the graphics, a thread for accepting input from the user, and a thread for the game's logic of like moving the ghosts around. And like, obviously, we've played video games before, and like, we're not waiting. Like, when I move the stick, it doesn't freeze the game to accept that, right? And so he says, that's a perfect example of, you might have these 3 threads, but the processor is going to interleave them together. And so it might be rapidly bouncing back and forth between them. But again, you got to consider that the multitasking context switch cost.
Yep. And I've definitely made this mistake. I think when you're bright-eyed and bushy-tailed and you first learn about these tools, you start doing all kinds of wacky, crazy stuff. When I learned how to, I think he talks about this he calls it granularity. It's like way later, I think maybe towards the end, I think the 7th chapter that we were reading. Coarse grained is where let's say you have 4 CPU cores, but you only have a single task. And so it's just using one of the CPU cores. It's not going to go across multiple. So you're underutilizing your resources at that point, right? Then he talks about like the properly matched tasks, which is, let's say you have 4 tasks and 4 CPU cores. Well, that's appropriately sized. You're not having to wait on anything. Those can run embarrassingly parallel. And if you overload them, it's called fine-grained. And fine-grained is where you are doing maybe overloading, and you might start hitting that context switching cost. Let's say you realize like, oh, cool, I'm going to write a web crawler, and it's going to have like, I want to do 1,000 sites at a time, right? That's fine, because a lot of that work's happening off the CPU. But when that stuff comes back and you're having to like context switch constantly across, let's say 8 CPU cores or 32 CPU cores, it may not be the best way of doing it if you're just bombarding the system with, okay, cool, all the stuff's coming back. And I will say, I'll give a hint. We haven't gotten into this yet in the book, but there's a really cool way of structuring this. It's called worker pools. Worker pools are a way that I can describe. I want to go to 1,000 websites, but you basically say, but only, I have 32 cores, let's say, but only process 32 of them at a time, right? So any of the 32 can pull in a new piece of work, and there's 1,000 in the work queue. But and you can do this not just for single CPUs. This is how we do it in distributed systems with a queuing system, where maybe I have 15 physical worker nodes, and each side of those physical worker nodes, each of them can do 32 processes at once. And so each one of them will say, okay, well, grab 32 things off the queue and then times 15, right? And so you can imagine now we're having this like larger and larger horizontally scalable work. If I realize the queue's getting too big, I can go and like add a bunch of workers to my worker pool. And, and this is where like AWS and Google Cloud get interested. And you're like, okay, well, if all my worker pools are full, add 5 servers at a time every 5 minutes until the queue gets below maximum threshold. Like you can do all kinds of cool things on top of it. And again, you've described your work in a nice concurrent way. You've got this embarrassingly parallel patterns on top of it, and you can start doing these kind of designs with confidence because you understand how to describe work in a way that can get done in large scale systems.
Yeah, but that's like you said, I mean, that assumes that our tasks are embarrassingly parallel. And part of that is good program design. We learned about that in Web Scalability for Software Engineers by Artur Ejsmont, the importance of making your server stateless so that, as you're as a user is kind of bouncing back and forth between different servers, whatever the load balancer is serving them up, that it doesn't matter which server the user is talking to. Now, if you're storing on that server particular state for like if that user is logged in or anything like that, that's going to be more challenging. But really, like, and I believe the book talks about this later, but like we're just talking about concurrency, but at a much larger scale, where like that's all really a load balancer and dynamically scaling amounts of servers are doing is, like you said, Nathan. I mean, spreading the work out across more computing resources.
Yeah. The pattern that he actually talks about too with this is it's a really well known one where you actually you fan out and fan in, and that is what a load balancer does, right? So I'm talking to a single load balancer, and a bunch of us are talking to this. So all of us are the fan out, all the users of a website, and we're fanning into a load balancer, right? And then it's fanning back out to a set of workload, a bunch of servers that are processing that data statelessly. And then those are probably fanning back into a database cluster under the back of it, right? And this is, you can see that these natural patterns of like he calls it fork and join in the data world.
Yeah.
And these kind of patterns are, and I'll tell you, this is a very useful way of doing stuff. If you've ever built a data pipeline, if you've ever used a tool like Airflow or one of these other pieces, you may have heard the term DAG, which is a directed acyclic graph, which is a way that you can say, provably, here's how data transforms across this graph, right?
Mm-hmm.
And a lot of times you always are looking for these embarrassingly parallel pieces where you're saying, okay, I kick off a job and I know I need 25 data sources that need to prep their data for this day's batch job. Let's say that it's telemetry data across a bunch of systems that the analytics team wants to look at. And so I don't need to go, well, give me the first one, give me the second one, give me the third one. What I do is I fan out until I trigger all these systems in parallel and I say, hey, for this time series data in this query call, give me this data and tell this downstream fan in or this join process that you're finished. And then the join process goes, okay, when all 15 data sources say that they're successful and complete, trigger the next part of the system, which is going to start processing this. And this is called an ETL or
extract, transform, load. We do a lot of this. My team at work, and this gets into what he calls like task decomposition, which is figuring out, okay, what is the nature of the task I need to accomplish, and how what is my ability to parallelize them. We do a ton of this at work because we consume a lot of data coming from the company, and then we standardize it in a form that lives within our application, and we expose it to our internal users to be able to query information about our external users' profiles more easily. And so, like MapReduce is a big one. Like the idea that, okay, every single piece of data coming in is logically independent from all of the other data, right? And for every single one of those pieces of data, I need to do the exact same thing to it. And so we're using like Google Data Flow, which is, a data pipeline tool. And so what we can do is we're reading all of this data from a Kafka queue, or I guess a Kafka topic. And it all comes in and we apply the exact same data transformation pattern to every single thing. And so with that, this is an embarrassingly parallel task. And so if our data flow pipeline starts to lag, we can just click a button and bam, we'll expand the computing resources. And, theoretically, we could have every computer in the world running this task for us, because there's just absolutely no need for any computing resource to know what any of the other computing resources are doing, which is pretty cool.
This is an interesting paradox too. This is an aha moment that I actually just found with a software engineer I was doing some architecture work with a new service that we're spinning up. And he had an aha moment because he hadn't done these like massively parallel things before. And I kept giving feedback on like, well, let's simplify this. Let's simplify this. And the paradox is the bigger the system gets, the simpler these components must be. You can do really fancy, complicated programming stuff if you're doing like a really simple web service on your own. But when you're scaling out, like MapReduce is a perfect example of this. If you actually look at what a map operation is or what a reduce operation is, they look like leak code challenges. Like they just look like really basic computer sciencey pieces. Mm-hmm. And the thing is, you want them to be, because it needs to be on this tight feedback loop of like, process this chunk of data, do this one, count that the thing, you basically go in and say, does it include this substring? Yes, count it, throw it into the next step, right? And it's doing that, of course, with millions or billions of pieces of data. And MapReduce, it's a really cool, and there's these new paradigms like, I say new, it's been out a while, but like Apache Spark, which kind of took MapReduce and then said, oh, well, we can do this for continuous data feeds, which is true, right? Maybe I've processed all this data up to a point in time, but it's really time series based data. And I'm really just trying to append data. I don't need to I don't want to reprocess all of the data for the last 2 years every night that I'm doing my big data pipeline. What I probably want to do is know that I got to some point in time and then continuously add these new things. And so I can query some intermediate data structure that says, okay, what's changed, right? What's changed? Or even if I need to know something about the last 30 days, this intermediate system that maybe has done the MapReduce or done these other steps can query this sort of intermediate data form and doesn't have to go back to the source data and do these very expensive MapReduce operations from scratch, right? And I think this is where, again, understanding these workloads, I find these puzzles, these are like really fun puzzles to work on. Because you go in here and you go, wait a second, like, is there a more efficient way that I can get what I want with these tools that I have, right? Like, can I describe the work in a way in which I'm like, oh man, if I had to do this from scratch, it would take hours. But because of the way we've structured it, I can query this really impactful, refined data continuously. That's cool. And that's cool because you can do this with like nice concurrency patterns.
Yeah, absolutely. But at the end of the day, it all comes down to understanding, okay, what problems are we trying to solve? Right. Because, you try to parallelize something that can't be parallelized, you're going to have a bad time. You try to run something sequentially that is embarrassingly parallel, you're also going to have a bad time. Lots and lots of really interesting stuff in this book. I think we've covered kind of the basics of the first 7 chapters. Nathan, is there anything you wanted to touch on before we kind of wrap up here?
No, I think this is a great overview.
Yeah, absolutely. Really, really interesting book. It's one of the ones where I think of the term, the term bike shedding is?
Yes.
Yeah. Bike shedding, if you're not familiar with it, right, is the idea that like a town council, right, they might rubber stamp the construction of a nuclear power plant because no one really knows how to build a nuclear power plant or what that goes into. So you say, yeah, sure, you take care of it. Everyone knows how to build a bike shed. And so you might get really into the weeds of how the bike shed is constructed and where it's constructed and all of that because everyone can speak to it. Sometimes I feel like with books like this, like it's the complete opposite of bike shedding, where it's all pretty technical stuff. This is not what I'm dealing with on a day-to-day basis. And so, I can't necessarily expound at length on every single thing that came in this book. And so, if you're listening to this and wanting to learn more, like pick up the book because we have just barely scratched the surface of everything that's in here. And there's lots of really, really cool stuff in this book. So yeah, please check it out. And we always like to reflect as we read through the books, and even if it's just half the book, what we're going to do differently in our career as a result of having read what we read. So, Nathan, anything that stands out to you this week?
Yeah, I really enjoyed. So we got up to chapter 7. Chapter 7 is where things are starting to get interesting. I'm actually really looking forward to the second half of the book. But he goes over decomposition patterns in chapter 7. So that's like how I would structure this work and break it up into tasks. Um, I appreciate these books in that it gives me better vocabulary to communicate with other programmers. And one of the things I'm doing right now as an architect is collaborating with another service on how they should do some of the course structuring. And they're also not using programming languages I normally use, right? So they're like deep in TypeScript world. And it's always a nice reminder of like how to describe things in a more general way versus like I would easily go up, oh, well, in Go, I can do it this way, or, talking about this. This is going to make it easier for me to communicate with these engineers on why we would decompose something in a certain way. And so, that's what I think, better general vocabulary and using that in my daily job. So I think that's what I'm going to be doing differently.
Nice. And I just want to understand concurrency in Rust better. Rust is kind of what I've been doing a lot of. I don't love Rust. I'm forming a begrudging respect for it. But it's I don't know what Rust's strategy for concurrency is. And like I said, like this is just not stuff I deal with on a day-to-day basis. Like the very fine low-level details of concurrency. But I should know this stuff, because I mean, again, this topic in particular was one that, like, when what motivated me to get my master's degree, I was just like one of those, like, I don't know what the internet is. I don't know how data gets from one computer to another. But then the other things that, like, I didn't know, I'm like, I don't know what a CPU does. I don't know what a thread is. I don't know what a process is. Like, what's going on here? And so, if you feel that way too, like, hey, no shame. We don't always learn everything we should. This book is for you. So, I check it out. And that's who I would recommend this book to. I say, if you don't have a super strong background in operating systems, this is a great book for you. It's a pretty easy read. We're going to read through it in 2 weeks here. If we, you could probably get through it in a week and a half. So I think this is this is a good bang for your buck book. So if you don't feel super strong on operating systems and some of those low level details, check this book out, because it could really help you out. How about you, Nathan?
Yeah. If you came from the same background that I did, which was I actually did know I was a systems administrator, and so like I actually did have a lot of exposure to processes and forks and networks and all these other things, but it was all kind of like learned it from the trenches, learned it from the streets, kind of standpoint. These books do a good job of making sure that if you have knowledge gaps, or maybe you're overconfident in something, or maybe you're missing a little bit of context. I agree with Carter that this is like, I think I wrote, any software engineer who wants to dig deeper onto these patterns of concurrency and parallel programming, this book will let you speak more intelligently about these things. Instead of it just being like, oh, I've done a few things and it's kind of cool, you actually go, oh, I did these things and actually it fits into this decomposition pattern, and that's awesome, right? So and it's one of these where you're like, it's going to give you core vocabulary. If you're interested in the topic, absolutely check this book out. This is such an approachable way to get into this topic.
Yeah, Kirill is one we'd love to have on the podcast. We'll see if we can get him on. That'd be super cool. But that takes us through this week. Thanks everyone for tuning in. We're back to a much more technical book, like Nathan said up at the top, right? Still trying to find that balance between what's technical, what's more career focused, what's even more general, right? Kind of like our thinking in systems or slow productivity type books. Someone did say on the YouTube comments of the thinking in systems episode, he's like, this was a really interesting episode, but you guys could have read Dune or something this week, because you
the way we dug into it. That's hilarious. and I will say, I'm not committing to when we're doing it, but one day we are going to do designing data intensive applications.
Yeah.
It's a big book. It's a big book. But
I would have slotted it for sometime this summer, except I have heard that later in this year we're getting a second edition. But that is a promise from us on the podcast that
We
we
will.
will do designing data intensive applications, but it might be like a 6 to 8 episode series. So
let's do it. I mean, I'm excited about it. I've been
We'll
wanting
do
to
it.
read this book, and and this is a great excuse for it. And I'm excited. Who knows? Who's the publisher of that one? I think it's
Martin Kleppman.
No, is it?
No, the publisher, not the author.
I think it's O'Reilly.
I think it's O'Reilly.
It's an O'Reilly book. So maybe we can get access to an early copy, and we can,
that'd be cool.
Version 2 comes out, we can start our series. That would be really awesome.
Yeah, we're excited to tackle that one. In the meantime, folks, you can find us at contact. Our email is contact@bookoverflow.io. You can find us on Twitter. I'm at Carter Morgan. The podcast is at Book Overflow Pod. Nathan and his work with his Functionally Imperative newsletter is at functionallyimperative.com. And yeah, just you can always, we love hearing from you. You can comment on the YouTube channel or on the YouTube video if you want to hear back from us. And thanks for tuning in, folks. This podcast is really fun to make, and so we're glad that it's reflecting with our listeners. And we hope you enjoyed the discussion, and we'll see you next week for the second half of Grokking Concurrency.
See ya.